Welcome to this video. In this video, I'll show visually the method given by Euclid in Euclid's Elements for finding a square with the same area as a given polygon. This method can therefore be seen as a method for finding the square root. I'll give an actual example and show how visually this can be done. Before we get started, please remember to hit the subscribe button and give this video a like. Don't forget to hit the alerts button as well so you'll know whenever I upload a new video. This video is therefore concerning primarily the result of proposition 14 of book 2 of Euclid's Elements. I'll be trying to stick as closely as possible to the techniques that are available to Euclid at that point to find the required square. It may be the case that as things progress, other techniques become available which are not available earlier in the work. I won't draw all of the construction lines that would be strictly necessary. There would be far too many such lines and the diagrams would very quickly resemble a bowl of spaghetti and become completely unworkable. I will, however, refer to the appropriate propositions which indicate that the various constructions can be made and how they can be made, at least in theory. The focus here is more on the how to do aspect and not so much the why. That is, I'm not setting out to meticulously prove everything that I do. For the full proofs of the propositions that I use, then I'd recommend that you refer to an appropriate version of Euclid's Elements. I typically refer to Thomas Heath's version, which is, by the way, in the public domain and can be easily found and downloaded. But it's not essential to refer to Heath's version. There are plenty of other versions that are freely available on the internet and are just as good. Of course, the methods of proof that Euclid uses may not be completely acceptable by modern standards. This is not my concern here though. So the shape that I'll start with in this video will be some irregular quadrilateral. The same procedure as which is shown in this video applies, in principle, to planar polygons of any number of sides with the obvious generalizations. Let's start with the polygon PQRB. We want to find a rectangle which has the same area as PQRB. This corresponds to proposition 45 of book 1. In fact, proposition 45 of book 1 allows for the more general case of finding a parallelogram with equal area to PQRB. The approach outlined in proposition 45 makes use primarily of propositions 42 and 44 of book 1, though other propositions are required also. Of course, we can split this shape PQRB into two triangles by joining the points Q and B with a straight line. This can be done by postulate 1. Euclid gives a method in proposition 42 of book 1, whereby, given a triangle, we can find a parallelogram in any given angle, which has the same area as the triangle. We don't need to complicate things unnecessarily, so we'll simply construct a rectangle with the same area as the triangle. So we want to construct, therefore, a rectangle that has the same area as the triangle PQB. This is done by bisecting the side PB at G and drawing a line perpendicular to PB through G. That is, the perpendicular bisector of PB. Propositions 10 and 11 of book 1 allow us to do this. Then using proposition 31 of book 1, we can draw a line through Q parallel to PB and intersecting the perpendicular bisector of PB in the point F. And using the same proposition, we can draw a line through B parallel to FG and meeting the line QF in E. Quadrilateral BEFG is of course a rectangle and moreover, it has the same area as the triangle PQB. Now suppose we have a line AB. I want to effectively replicate the triangle BEFG, so it's in the position shown in the diagram where ABE forms a straight line. In fact, Euclid, in his proof of proposition 44, speaks of placing the rectangle BEFG so that AB is in a straight line with BE. Euclid gives no indication about how this placing is to be done, so we'll have to improvise a way which isn't too difficult to do. Extend the line AB sufficiently far. This can be done by postulate 2. And cut off the length BE, which is of course equal in length to the side BE of the rectangle. This can be done by proposition 3 of book 1. Now draw a line perpendicular to ABE through B by proposition 11 of book 1, extended sufficiently far, and cut off the length BG from this line, equal in length to the side BG of the rectangle, again using proposition 3 of book 1. Using proposition 31 of book 1, draw a line parallel to ABE through G, and a line parallel to BG through E, meeting in the point F. Thus we've replicated, or placed, the rectangle BEFG in the desired position. Extend the line FG and draw a line parallel to BG through A meeting the line through FG produced at H. Draw a line through HB and extend the line FE to meet the line through HB in K. Draw a line through K parallel to EB and extend the lines GB and HA to meet the line just drawn through K in the points M and L respectively. The area of the rectangle ABML is equal to the area of rectangle BEFG. Some of you may have realised that I didn't actually need to do quite as much work here as I have done, but nevertheless in what follows, the preceding steps will be necessary, and so for various reasons it just made more sense for me to illustrate them here. This process is now repeated for the triangle QRB of the original polygon. I'll just show the steps on the screen without any explanation, since the steps are, in principle at least, identical to the steps taken for triangle PQB. So now we have a rectangle which has area equal to the original polygon. Extend the line AD sufficiently far and cut off a length dx which is equal in length to DE. Proposition 3, Book 1 allows this. Now bisect the line segment AX using Proposition 10 of Book 1 at the point C, and using Postulate 3, describe a circle with centre C and radius CX. I'll only show the upper semicircle here. Produce line ED sufficiently far to intersect the circle at the point F, and then using Proposition 46 of Book 1, construct the square on DF. The square DFGH has the same area as the original shape PQRB, and this completes the construction. Therefore, the side length of this square can be thought of as the square root of whatever number represents the area of the polygon PQRB. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.